Okay, so today we are going to finish chapter 11.9, or power series representation. This will be a little quick video, maybe like 15 minutes. I just want to talk to you guys about the last pieces, and then I'll send out another video for you of Taylor and McLaren. That'll probably be a two-part video as well. But basically, for this one, we're going to finish up a last little piece of power series representation. We can, perhaps I can make another video involving some practice problems or whatever, just to give you more practice. But there's a theorem I want to revisit. It says, recall that for an alternating series, we can approximate the error in the sum. Okay, so if S, the sum, is equal to the summation of -1 to the n, b sub n, from n equals 1 to infinity, and b sub n plus 1 is in between 0 and b sub n, so meaning that b sub n plus 1 is a positive number and it's smaller than b sub n, and this is a way of saying that it's a positive decreasing series, and the limit of b sub n is equal to 0. So these are the two, kind of, when I taught you guys alternating series, these are the two things you had to check off to guarantee that it was a convergent series. So they're basically saying make sure that it's a convergent alternating series. Then we can say any partial sum S sub k differs from the actual sum S by at most b sub k plus 1. Okay, so we're going to kind of go back to that. So let's say that we have the actual sum, which we do not know, and the partial sum, which we're just going to make up at stopping at k. We're going to subtract those two things. Okay, and when you take two things that are very close to the same, or they are the same, their difference becomes 0. Okay, so what we want to find is, by subtracting these two things, subtracting these two series, the partial series and the true series, we want to see if we can approximate how close they are together. Okay, so if we take S minus S sub k and we get a very, 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 very small number, then you can say that S sub k is very close to the true sum, the actual series sum, okay? You don't say that it's equal to that, you don't say that it's exactly that, but you can say that it's really darn close, okay, based on the error you decide. So all I did was I wrote right here, this is the original series S, and then this is the partial series, or the partial sum, up to k, so S sub k, right? So I subtracted them and I turned them into their summation notation. Now think about this. If you wrote out all the terms of b sub n, wouldn't it be b sub n plus 1, b sub n plus 2, b sub n plus 3, b sub n plus 4? And then if you wrote out all the terms of b sub n from 1 to k, it would be b sub n plus 1, b sub n plus 2, b sub n plus 3, and you would go all the way up to k, right? So think about this in your mind. Oops. If you wrote this out, this would be b sub n, whether it's plus or minus, let's just start off with minus. So minus b sub n plus b sub n plus 1 plus, minus b sub n plus 2, all the way. And then you would subtract off, then this would be -1 to the 1. So this would be negative b sub n plus b sub n plus 1 minus b sub n plus 2 plus b sub, plus all the way up to b sub k, right? Because you're stopping at k. That would be the last term. Okay, now notice this minus sign is going to distribute to everything, right? So that means that our b sub n will become plus b sub n, and it will cancel this guy out. Then our b sub n plus 1 will become minus, and it'll cancel this guy out. Our b sub n plus 2 right here. So what I'm doing is I'm looking at these terms. Because I'm subtracting them, they're going to cancel out the terms that came before in the original series. But they won't be able to cancel anything after b sub k, right? So the last term in this series, or this sum, is b sub k, okay? So it'll cancel everything out up to b sub k. So what will the next term be? So we come over here. And I think I have a typo in here. Let me fix this typo real quick. So right here, oh no, it's okay. It's in a different notation, so it's okay. So I want you guys to look at right here. I changed the starting point. So the leftover series, after everything cancels, the leftover series will start at k plus 1. Whatever the term is after the k term, that's where we start having the leftovers. Okay, so that'll be n equals k plus 1 to infinity. So this is our new series. Okay, and if I wrote all these terms out, I would have b sub k minus b sub k plus 1, you know, so on and so on. And now it really doesn't matter. Somebody might say, well, what if the first term was negative and the next term was positive? It really doesn't matter because you're doing absolute value. All you care about is how far apart they are from each other, okay? But what I do know is that b sub k plus 1 is the biggest term in these components, right? It's the biggest one left because it's decreasing. So that means every one after it is smaller than the one that came before it. So b sub k plus 1, whatever its value is bigger than all the rest, okay? Since it's bigger than all the rest, that means that this portion right here will make b sub k plus 1 a little bit smaller than it used to be because you're either going to be adding to a negative or subtracting from a positive. But either way, b sub k plus 1 will be smaller than it used to be. So that means that we can say definitively that this will always be less than b sub k plus 1. So whatever terms are left, however many, 1,000, 10,000, 100,000 terms are left in your series or however far you want to add up to, you know that all of those added up will always be less than b sub k plus 1, right? Because they're taking away from b sub k plus 1 because they're all going to be opposite signs because it's an alternating series. So if b sub k plus 1 is positive, then when you subtract b sub k plus 2, it'll now be smaller than it used to be. If b sub k plus 1 was negative, then that means that guy would have needed to be positive, and b sub k plus 1 would still be smaller than it used to be, okay? So in all these cases, we know that this, whatever this sum is, the absolute value of it will be less than this term, the b sub k plus 1. Well, then that means that this guy way up here will be less than b sub k plus 1. So that's what I wrote right here. And that is what we're going to use in this next problem. We're going to use that idea. That's the error term, right? That's the term that says that everything before it, that comes before it, is this close to the partial sum. So if my error term was like 1/750th or, you know, 1/10,000th, okay? So let's say that my error term was 1/10,000th and it was the 7th term. That means that if you add up the 6 terms before it, you're going to be within 1/10,000th of the actual sum. You won't have the correct sum. You won't know how much the exact sum is, but you're going to be within 1/10,000th, maybe better, but you'll be within that much. Okay, that's the guarantee. Okay, so if we have an alternating power series, then we can use this estimation theorem again. Okay, so how many terms are needed to estimate from 0 to 0.3 of 1 over 1 plus x cubed dx? Now, this might be, you might be looking at this and trying to figure out how can I integrate this? Well, you probably can't. You could use a calculator to estimate, but I don't see any straightforward approach that I've taught you this semester that would work on this. Not integration by parts. It's not some kind of arctan. I don't think it's completing this work. I don't think this problem can be done with normal integration techniques. So what we're going to do is we're going to convert it to a power series, and that's kind of the I hate to use the word power, but that's kind of the power of a power series is it's just addition or subtraction. So if you can convert something to a power series, then you might be able to estimate it. Okay, so we know that this guy, 0, oops, sorry, not that. We know that 1 over 1 plus x cubed, that's an easy power series now, right? We now know how to do that pretty well. This is going to be the summation of n equals 0 to infinity of, what is this? Negative x cubed to the n. Does that sound right to everybody? Are you guys okay with this? So then that means that this is actually negative 1 to the n, x to the 3n, right? From n equals 0 to infinity. So now what if I were to go and integrate this, right? So if I integrate this, I taught you in the previous video that you could now integrate this, and you now have the integral of 1 over 1 plus x cubed dx, okay, is equal to the summation of n equals 0 to infinity of -1 to the n x to the 3n plus 1 divided by 3n plus 1. Remember, we just go straight to the x term, or I shouldn't say the x term, but the x variable, and we integrate that, and we get 3n plus 1 divided by 3n plus 1 plus some c over here, okay? So now what I'm going to do is I'm going to write it out as an definite integral. And I'm going to write out some terms. So let me see here. If we plug 0 in, we get x over 1, right? This would be x over 1 to the 1. If we plug 1 in, we would get minus, what was that, x to the 4th? X to the 4th over 4. Plus, we plug 2 in, we get x to the 7th over 7. Well, this is kind of a nice pattern. I'm starting to see it now. X to the 10th over 10, plus so on and so on and so on. Okay, so now we're making it a definite integral. Okay, and I'm going to integrate this definite integral from 0 to 0.3. Okay, so that means I'm literally, quite literally, going to take 0.3 and plug it in for x. Now, luckily, they gave me 0 right here, so that makes my life a little easier. In general, I would try to stick to that for you guys. So that means the integral from 0 to 0.3 of 1 over 1 plus x cubed dx is equal to 0.3 minus 0.3 to the 4th over 4 plus 0.3 to the 7th over 7 minus 0.3 to the 10th over 10, so on and so on and so on, right? So that's what we have, okay? So what we're looking for, just like in the alternating series, is we're trying to find a term that is smaller than that term, okay? So we need to find the first term in our series, or in our sum, that is smaller, I guess our series, that is smaller than 0.0005. So on my calculator, I could take, and I would do, I'm pretty sure it's probably not this guy. It's either this one or this one. And it might take more terms, but normally I can do by inspection. If I do 0.3 to the 10th or I do 0.3 to the 7th, I'm getting really small numbers, because remember, you're doing 0.3 times 0.3 times 0.3 times 0.3. That's going to move the decimal each time to the left, okay? So I'm just going to first check 0.3 to the 7th. So let's do 0.3 to the 7th over 7. So this is 3.1243, I guess, times 10, if we do 4 decimal places, to the -5. So that is equivalent to 0.0000312243. 1, 2, 3, 4, 5. Yep, that's it. So that means that this is worth about that, approximately, I guess you could say. And then that is exactly that if you round it off. So 0.00003 is less than 0.00005, right? It is smaller than. So that means that our error term is this guy. That's our error term. So we need 2 terms in order to be 2 terms in order for our sum to be within 0.0000312243, or you could just say 0.00003. Okay, so did we get the desired accuracy? Yes, we're actually better. We're within 0.0003. They only wanted 0.0005. Okay, now if they wanted to, we would say, what is our approximate sum? So then all you would have to do is you would just add the first two terms. So we would do 0.3 minus 0.3 to the fourth divided by 4. And I get 0.3 minus 0.3 to the fourth divided by 4. I get 0.297975. Okay, and this is within 0.3 to the seventh over 7. Okay, so this is our error. And this is our estimated sum. Okay, so that's how we can use the alternating series to help us with approximating sums. Now there's other techniques. There's the Lagrange remainder, and that's working with Taylor polynomials. There's all kinds of stuff you can do, but if you ever work with a Taylor polynomial and you get an alternating series, then you can just jump straight to the alternating series technique for the remainder theorem. Okay, so that'll be it for this video. I just wanted to make a quick one to finish up chapter 9 for you guys and send it out. I'm going to send out Taylor series probably later on today or tomorrow, so we can talk about that, and then we'll have our exam coming up pretty soon.